Planetary data for mapping. This is just a brief overview, both of the type of data that we are normally using to do, like, let's say, photogeological mapping, but also a bit of spectral mapping. And I will talk about how the data appear, how they are acquired, and also how you can download them. So it will be about the data and also the repositories. It doesn't, I mean, I don't have the aspiration to be the most complete talking about the whole data repositories, because you will see they are very much, there are many. But at least I would like to touch the most user-friendly ones for planetary mapping and cartography. So, moon data. So you will see that the day after tomorrow, we will deal more specifically about the moon, and we will start to build up our very first moon map. And so, very briefly, moon data. So there are quite a few missions providing useful data for geologic mapping on the moon. The most, let's say, famous ones are data acquired by the Lunar Reconnaissance Orbiter, LRO. We have like large scale data and narrower scale data. Large scale data are usually lower resolution, but encompassing the whole planet, like the LOLA, which stands for Lunar Orbiter Laser Altimeter, is a laser altimeter orbiting around the moon and shooting a laser and then gathering the topography of the whole satellite. And then the ROC camera, which is the Lunar Reconnaissance Orbiter camera, which is a package of two instruments, the WAC, which stands for wide angle camera, and NAC, which stands for narrow angle camera. You will see these acronyms all around, let's say, the planetary science, because these are very commonly used to many missions. Simply stand, how large is the field of view of a camera observing the surface of a planet? And together with this, the size of the field of view goes also the resolution. The narrow is the angle camera, the higher is the resolution normally. Then another important instrument that you will see also the next day is the Selen Kaguya, which is a Japanese mission from JAXA, particularly the terrain camera, which is a camera with stereoscopic capabilities, providing images and also stereo reconstruction of the terrain, and then multispectral images, which is providing multispectral images with the mineral percentage abundance. There are quite a few moon data repositories. For example, if you want just to consult the data and just have a quick look, you can use Google Moon, you can use the Orbital Data Explorer to use a map-based search to search for data, both for images and also spectral images, the Pilot image locator tool, a Rocket map, and many more. So first, I would like to talk about the Lunar Reconnaissance Orbiter very quickly. It's a mission that has been launched in 2009 from Cape Canaveral, and it embeds quite lots of instruments, not only imaging instruments, but also others. But the ones we are more interested on are the WAC, wide-angle camera, as I said, which has a resolution at the ground on the moon of 100 meters per pixel. So one pixel of a picture, of a resulting picture, is 100 meters wide. And the NAC, so the narrow angle camera, has a much higher resolution, up to 0.5 meter pixel, or even more at certain places. Then, of course, you have LiDAR-based topography, the LOLA, whose, let's say, gridded data. So after shooting the laser, the data are going to be interpolated and gridded, and the grid size is around 118 meters per pixel, which is good because it also, let's say, closing some gaps of the WAC images that is also observing in stereo the moon. And sometimes when you reconstruct stereo topography, the shaded areas cannot be resolved with stereo topography, but can be resolved with the laser altimeter. And then also other instruments, for example, the thermal maps for cold charts with a diviner, and so on and so forth. This slide is just to provide you an overview of how the NAC, narrow angle camera, looks before being integrated in the satellite, and of its performance. So this is a very slanted angle picture of the central peak of Tycho crater, which is a beautiful crater that you can also observe from the Earth. When the moon is shining in full moon, it's very bright with very widespread ejecta rays. And you see that the central peak has a very defined shape, very sharp, with this impact melt touching sharply the margins and the slopes of the central peak. You got some cooling cracks, probably of the impact melt, some small impact craters, and the shadows casted by the central peak inside the crater itself. But then you see that I put here a small square, and if we enlarge it, we see this boulder here. Oops, sorry. So this boulder here is the size of a building. It's like it's more than 50 meters wide. It's it's like a 4 or 5 story building, and it's full of cracks. It's very bright. And how come that a boulder is on top of a super sharp mountain? You see here, just at the top of a mountain, you get a very big boulder. Probably the explanation is that this boulder was ejected after the transient crater formed, and then the central peak emerged, and then went down after jumping up, after being shot into space, just went down and falling on the top of a newly formed central peak. And with the narrow angle camera, we can really observe also the cracks and the fractures that were created after the bouncing back of this boulder, and then also other cracks and fractures all around, small boulders, some loose material on the flanks, and so on. So this is just to provide you an idea of how well we can look at the moon with this camera. And this camera also observed, and you will see the next days, the landing sites of the astronauts, the Apollo astronauts on the moon. You can really go and search for NAC pictures of the Apollo landing sites, and you will see the tracks of the astronauts going around the LEM, and where they deployed some instruments like laser reflectors and so on and so forth. So very super powerful instrument. Also good for very high detail analysis. So a good way to search for lunar data, and this is a specific repository for LROC, is the QuickMap. So I will give you a short demo, and you will see, you will get then later the presentation. So if you open up the QuickMap in your browser, you will get this orthographic view of the moon, but you can choose here with a button the type of projection that you prefer. You remember from Angelo's lesson that we will have many projections. One can be the equidistant cylindrical, that is taking up the moon until the 75 degrees of latitude, north and south. So basically we are lacking the poles because they are too stretched. You see that the craters and markers are very much deformed. You can go to stereographic North Pole. So here we can observe the lunar North Pole. Okay, same way the South Pole, which is now very interesting because there you have like the Shackleton crater, which is one of the possible landing site of the Artemis 3 missions, and then so on and so forth. If you want to have some data about the moon, let's try to look for example, Copernicus crater. We can zoom in with your mouse wheel, and then you can go to the search tool, and then you will get some options. You can pin a point, you can draw a line, or you can draw a polygon. If you draw a polygon, your cursor becomes a point. You can simply click around the crater or around the area that you want to download the data from. You double click, you will get a prompt with a summary product that is taking inside all these layers like clinopyroxene abundance, FEO abundance, roughness maps, very low resolution. It's up to 256 by 256 pixel per degree in this case. Here it's calculating the layers again. Here it's the ground resolution. So this is a summary product with lots and lots of layers, but a very low resolution, like around 400 meters per pixel. If you want to search for more high-level products, you have to go here to search, and then here you have, for example, the ability to search for MQ data, so compositional data, and then NAC images. And here you will get all the NAC images inside this polygon that I just drawn. Of course, there are a lot, so it takes some time from the server to provide us an answer. If it takes too much time, we can move forward. There are also pre-prepared mosaics, like, for example, regional mosaics, which are targeted, so they are not covering all the locations. You can toggle the footprints, so you will see how the mosaics appear inside the selected area. You will see that this area is very much well covered. If you click on top of one of the mosaics, you will see the footprint like highlighting, and then you can go and select it. You will get a link. It's opening up a new page, and you will have like more information. You are able to download the lower resolution mosaics at 20 meters per pixel if you want to do, let's say, a broad scale analysis of 5 meters per pixel or even more. For example, the real mosaic, it's here, 1.3 meters per pixel. If you click for more information, you will jump to a page where you have, again, your mosaic displayed, and you can get like the high resolution data or even the raw data in PDF format. This is a quick overview. You will get the information also in my presentation. If we jump back to this page, you will see that I basically skipped this button here. This is a layer button. If you click it, you will get a global features map. This is basically what are the global products that you see here, but just displayed live. For example, there is the grail for the crustal thickness model of the moon. You can toggle this layer, and you will get the model of the crustal thickness. And this can be consulted live into the quick map, or for example, the gravity anomaly, or global DTNs, titanium abundance. Let's have a look at titanium abundance. Yeah, we can switch this off. This is the titanium abundance of the moon. You see how much titanium you have in the lunar maria, for example. You will see it later on, probably next days in other presentations. But this is just a very, very quick way to consult the data and also get an idea where to focus your attention on. Then you can download the summary product here or search for specific maps here. So this is a good way to start looking at the moon. So if we jump back to the presentation, you will see that we have a very similar tool using the same framework for Messenger. We will not deal with Mercury for this specific school, but it's good to know if somebody of you is working on Mercury that the quick map is also available for Mercury, and it's basically working the same way. You have lots of layers and you are encompassing a lot of information. And it works basically the same way. I left you the link for your convenience if you want to explore it. Mars data. Very, very quick overview of Mars data as well. Lots of missions providing useful data for Mars. You will see how much more missions you have for Mars. You will get Mars Global Surveyor, which is a late 90s, early 20s mission where you have the MOLA. It's sounding like the LOLA, so it's like Mars Orbital Laser Altimeter. So it's also a laser altimeter orbiting the planet, shooting laser, getting back the altimetry, and then creating a beautiful topographic map of the whole planet. A high-resolution camera, one of the first in orbit. Mars Odyssey, which has a thermal emission camera, which is creating thermal emission images, and you will see later on. Mars Express, who has the HRSC camera and Omega spectrometer. It's fairly old mission, but still performing pretty well and still ongoing, I think, until today. And I think that they are now evaluating whether to renew this mission or not. Mars Reconnaissance Orbiter, which is basically the companion of the Lunar Reconnaissance Orbiter, but of course orbiting around Mars, providing the higher resolution images that we have of this planet so far. And the ExoMars TGO, which is actually 2016, this date is wrong, and it's still ongoing, which has a Cassis camera, which is providing colorful images in stereo capabilities. You will see lots of this data on Thursday in the Mars hands-on activity. Of course, you will have lots of repositories on Mars, even more than on the Moon, possibly, because you will get a very, very high variety of data. Here I've listed some of them, and you will see them later on. And now I will like to show you a bit also how the Mars data are going to appear. So this is the MOLA. MOLA, this is the global topography of Mars. You will see that it orbited the planet. It created a beautiful topography of the poles, of all the major structures and features around Mars. And you can see basically the shape of the planet at full scale. And it's really quite impressive. Also thinking that it's more than 20 years old now, and it is still the reference for every data that you get around Mars. And I guess this is the same for the Moon with the LOLA. So once we have constructed our global topography of a planet, then all the other data is referenced on top of this planet. If you are creating stereophotogrammetry with high resolution images, you have then to record them and adjust them to the absolute altitudes together with the laser altimeter. All the laser shots that are being interpolated inside this map are actually single laser points with a precision of 3 centimeters on the surface. So every other data that is constructed around the planet is referenced to this surface. This is a very nice image I want to show you. You have seen beautiful colored images, but how do the real data look like? And so here, this is how the data look like after the orbiting of the satellite. You see that a lot of gray stripes made of very, very tiny dots that are basically crossing each other. These are the single laser shots taken around Mars. And all these observed vertical stripes are actually the orbits of the satellite that was going around Mars, shooting laser points onto the surfaces of the planet. And each point has a specific location in latitude and longitude and altitude. And the altitude, as I said, has a precision of 3 centimeters. But of course, you will see that there are also gaps. Sometimes there are gaps because not all the orbits are crossing the same way. So where you have gaps, you have to interpolate the data. So to, let's say, invent the data in between one precise point and the other precise point with the very, very sharp and accurate altitude. In between, you have to interpolate the data. And of course, this is basically creating an average of the topography and altitude at these places here. But nonetheless, this is very, very much useful to calibrate all the other data onto the planet. And then you will get the possibility to, of course, have the whole physiography of the planet if you are constructing a very, very large map, for example, a global map of Mars or a global map of a huge province of Mars. This is a very good place to start. You will get also the shaded relief, of course. You can do all the calculation that you can do on topographic data, calculate the slopes, calculate the aspect, and so on and so forth. Very, very useful data, and the basics that you need to have in basically every product or every mapping project that you build around Mars. I said that you have also the very first camera on the Mars Global Surveyor, which was the MOC camera, which stands for Mars Orbiter Camera. It's a panchromatic camera, so acquiring, let's say, in grayscale. In grayscale, with a resolution between 1.5 meters and 12 meters per pixel. You have to imagine that in the late 90s, this was a big deal to observe features 1.5 couple of meters large on Mars. And since it was observing the surface of Mars around different orbits with a fairly slanted angle, the perspective was changing, and you can put together 2 images with a baseline separation and get stereo capabilities. So the angle of observation of the same spot from 2 different, let's say, points of observation gives you the possibility to reconstruct stereo topography at a high resolution. So this camera was able to the stereo topography, which was, of course, then referenced on top of the MOLA data. Of course, this mission has ended, and this camera, since it was acquiring quite a high resolution data, the data volume to be stored inside the satellite 20 years ago was a lot. This is the coverage of the camera around Mars. So every yellow dot is a single frame of the camera. So you have to imagine that if you are acquiring high resolution data, taking up a lot of space in, let's say, in the memory of the satellite, you have to target them. You cannot simply expect to go around the planet and shoot images all around. You have to prioritize and target your observation. You will see, for example, that the Valles Marineris here, the huge canyon transecting the equator of Mars, was observed a lot. A bit less just on the south, was observed a lot in the flanks of the Olympus Mons, in the 3 Tarsis. The topographic dichotomy was observed a lot. Some craters that were relevant for example, targeting the landing of the Mars rovers, Mars exploration rovers like Opportunity and Spirit. For example, this is the landing area of Opportunity in the Meridiani Planum. So just a general rule of thumb, if you have a very high resolution data taking up a lot of data volume, you will have to expect gaps in the coverage because these have to be targeted and prioritized. And this is true for every mission. Mars Express. Mars Express is an ESA mission, very important for many reasons. One of these is that you have on board the high-resolution stereo camera, HRSC. It's a very complex instrument. You will see it here in our optical bench before the integration of the satellite. It has inside lots of different channels and telescopes and instruments. And basically, it's observing the surface of Mars along the track of the orbit in many different ways. One of them is observing the surface of Mars on nadir. Nadir means on the very, very vertical. So you will get a vertical image of the surface of Mars. Then it has also a color filter. It is observing the surface of Mars in blue, in green, and the infrared. And combining this together, you will get a very, very colorful information about Mars, also highlighting the presence of some minerals that you basically will see everything in red in the, let's say, in the visible spectrum. Then stereo channels. So while observing a long track, you are observing the surface from one direction and from another. You put them, the two together, and then you will get the stereo DTM, so the topography. The topography was previously reconstructed at 100 meters per pixel, although the resolution of this instrument is 12.5 meters in the imaging, in the real pictures. The SWOT is the frame of the camera. It has a width, which is 52 kilometers, and the length, which is around 300 kilometers minimum. So basically, these are the stripes that are observed, and then they are made available as single products. You, of course, get a lot of information pre-prepared by the team. Nominally, these are what you get. So blue channel is called BL4, so the fourth level of processing, the one available to the public, cleaned by the noise, map projected, and registered with the DTMs. DA and DT are the two types of DTMs. Green is GR, it is the green channel, IR is the infrared channel, ND is the nadir channel, and RE are the left and right channels of the stereo observations. Nowadays, a good way to download HRSC images is to use another portal that I will show you later on, which basically is encompassing and taking all the images together, creating multi-orbit data. This is how it appears when you construct the topography in the visible channels of Mars. You will see a beautiful crater that is impacted on top of an outflow channel with lots of beautiful islands shaped by the flow of water, some cracks and canyons. So very, very beautiful stereo reconstruction capabilities. This is the coverage until 2016 of the topography plus nadir channel plus color channel. So where you have all the data together. As I said, now the team is reworking all the data, and you have a WebJS, so a web interface with a map-based view, where basically they are not taking single, you cannot download a single product, but they have created tiles of reprocessed data, where you can download a square tile with a higher resolution topography, so double the resolution of what you had previously, also with color capabilities and I mean, it's much more cleaner and much more convenient for analysis. But this is also what you can download. So there are many ways to download data. CTX is on board the Mars Reconnaissance Orbiter, the mission that was orbiting Mars since 2007. And the acronym stays for Context Camera. So the name speaks for itself. It gives context to high-res images, which I will show you later. This is the telescope, so the actual instrument, which is quite big, and it provides a resolution of 6 meters per pixel. So you will see it's double the resolution of the HRSC of Mars Express. HRSC was 12.5 meters. This is 6 meters, and actually can arrive up to 4 or 5 meters. So we are doubling the resolution. This is a few years younger than HRSC. It's doubling the resolution. It doesn't have stereo capabilities, doesn't have color capabilities. It's just observing in panchromatics or in grayscale, but double the resolution. The SWOT is similar. So the footprint, the frame that you're observing on Mars is similar. It's 30 kilometers wide, more or less, and the length is variable between 50 and 300 kilometers. So it's quite good. I said this has not stereo capabilities, so it's not observing the surface of Mars at a specific angle before on one side and then on the other side, moving along the track. But since this camera is orbiting Mars for 15 years now, it has a good chance that some frames overlap one with each other at specific angles. By the way, this is how a mosaic of such images appears, so it's very good for mapping, and we will use it a lot on Thursday. This is the coverage. So you see in 15 years, basically they have covered the whole surface of Mars. And covering, as I said, the whole surface of Mars, you will get the chance of overlapping images. If you have overlapping images, you can try anyways to reconstruct the topography. The quality of the result is highly dependent on how much is the separation between the two images, and so the stereo angle, so the ability to perceive depth by the software that is reconstructing the topography. But nonetheless, this is proving to be a quite good instrument to reconstruct topography anyways, although it was not designed for that. So it's a good thing to keep in mind. So HiRISE is basically like the king of the cameras, you know? It's the highest performance camera that we have on Mars so far. And it's providing lots of data. The ground resolution is 0.25 meters per pixel. So basically a pixel is this big, yeah? It means that you can observe objects this big, or as big as your desk, as big as your car on Mars. And actually, I'm not saying as big as your car just by chance, but this is because they are using this camera to target the position of the Mars rovers, like the Perseverance or Curiosity rovers on the surface of Mars, to plan the traverses of the rovers. And how does it work? This is the sensor of the camera. By the way, the telescope is huge. You see, this is a person. This is a telescope. It's 70 centimeters large, the mirror of the telescope. So it's really a big deal. And this is the instrument, the whole instrument. So it's basically as large as a satellite. This is one of the images that can also be acquired in color composite, as HRSC are in red, blue, green, and near infrared. And the near infrared channel is the one that is, if you color composite in a specific way, color in blue the presence of sand or a basaltic material all around Mars. Also stereo capabilities. So observing the surface of Mars at different angles, you get the possibility to stereo topography. So you have to imagine that such high resolution, you will get a DTM topography of 1 meter resolution. So you really can observe very, very high details in the surface of Mars, both in images and in topography, so in 3D. And this proves to be very useful, for example, for those doing stratigraphic analysis on layers, so like calculating the altitude, the orientation of layers, calculating the migration of sand ripples in the surface of Mars under the action of the wind, and other surface changes related to the seasonal variation. So how does it work? Just very briefly, this is the sensor. And these are basically small CCD sensors. So you don't have to imagine like a sensor of a normal camera. This camera have to be thought like a rake, okay? This is scraping the surface of Mars. And every of these small stripes is a framelet. Is a CCD that is acquiring a specific stripe on the surface of Mars. So this one, if you're moving around the surface of Mars, is acquiring this small portion of the image. The next one is acquiring the next one, and so on and so forth. And you see there's a small overlap between them. So after it acquired all these small portions of the image, and you have a small overlap, you can then mosaic them together, register them together, and then create the final image. And you see that the central part has also these greenish ones and also these reddish ones. So this is actually the green and blue channel and the near infrared channel, meaning that you are acquiring the whole width of the SWAT or the HiRISE camera in red color. Okay, why red? Why red wavelength? Because Mars is red. And since Mars is red, if you acquire using the red wavelength, you will get the less noise, signal to noise ratio, meaning that the images are cleaner, basically. You will get the most clean image of the surface. The central portion has also these other two CCD in blue, green, and near infrared, meaning that if you download the HiRISE images, it's all black and white, apart from the central strip that you can download it separately, which has also the color information, the one that I just shown before. So this one. So you have a wide framelet, a wide frame, sorry, but the inner two framelets are mosaic together in colors. And you see how you can mosaic them, and you get also this color image in between. The SWOT size is typically 12 by 6 in the red channel, so 12 kilometers in length by 6 kilometers in width. And the red, IR, and blue-green are just 1.2 kilometers wide. So if you want to use the color, you have to be lucky, of course. You have to have your features just inside the image. But of course, you can ask for an image. There is a website, which is called HiWish, where you have to provide your rationale and the location for a specific target that you want to be acquired. And then you are put into a queuing list. And eventually, if the instrument team is prioritizing as high priority this scientific significance or the scientific motivation of you wanting to acquire a specific image in a specific location, they're going to take it for you from the satellite and provide to you the image. It can take sometimes, typically months or even a year. But if you have a very, very sounding motivation or scientifically relevant motivation, you will get into queue, you will get your own image. So it's a good way to also plan your scientific activities in short or long term, let's say. Some examples of what I said before. So this is an image of Gale crater in color composite. So the central strip of a high-rise frame in the color composite that is emphasizing, say, the mafic material in bluish. And if you look closely here, you will get the black dot, a bit shiny. This is the Curiosity rover. And if you look closely, you will get also the path of the rover. Steering points, here you get the path, steering point, yeah, all the path of the rover. So, as I said, this instrument is also used to plan the paths of the rover, analyze the types of risks that is going to encounter. For example, slopes, boulders abundance, if you are getting through, say, a sand pit or some dunes, so to evaluate and assess the risk. We will go to talk about this on Thursday more specifically, where we will use high-rise data to analyze the Traverso Perseverance rover so far and try to guess where we could go and observe more stuff on G0 crater. But this is the idea. You will get color images, very, very super high resolution stereo topography. You put them all together. You pre-analyze the path of the rover, and then you start planning the path. And then you will also help yourself with the cameras of the rover that you observe the ground truth on the surface of the planet. So you have always this double check. Another thing that you can do, as I said, is observe the surface variations at very, very local scale in different times of the year. So, for example, this is the so-called RSL. This is the recurrent slope lineae. It's basically a solid flux of dry sand that is probably caused by the sublimation of some clathrates of some very, very salty ice that in the spring of Mars, in the south-facing slopes of craters, is sublimating and releasing, say, dry sand on top of this dust coating and creating these very, very black strips of dry sand. So this is another nice thing to see. And then, of course, you can observe sand ripples moving and then infer the motion of dunes on the surface of Mars under the action of the prevailing winds that are still acting nowadays. I talk about topography. This is how it appears. So you see again the RSL. These small stripes here are the stripes made up by the dust levels. So the small whirlwinds that are passing through the surface of Mars, just creating their own path around. And the nice thing about the high-rise is that the team is providing the topographic models already pre-prepared for you. Of course, not all the images that high-rise is taking because they are too heavy and they are too much, but at specific places, you will get the pre-prepared product for you by the team, which is assuring you also the quality of the result. So I said that you have these images that are quite high resolution, let's say 20 centimeters resolution. You have to imagine that they are taking up a lot of disk space. They are very heavy. And this is why the coverage is so limited. Okay, I said about the mock before, you have to basically all the time balance the disk space or the memory space you will have on board the satellite. That also has to be, let's say, balanced also with the other instruments. Also, you have to take into account the transfer data rate from Mars to the Earth, which is not fast. And so you have to really target and prioritize in a very, very careful way where to observe the surface of Mars. And so you see that the coverage is quite limited because you have to imagine that every red dot is a single frame of high rise weighing up 1.5 gigabytes. So you have to imagine that you have to acquire 1.5 gigabytes of images on the surface of Mars. You have to store them in the memory of the satellite, and then you have to transfer them to Earth. It's a very, very long endeavor. Takes a lot of time, and this is why the coverage is limited. So also, if you want to ask for specific images and observations, you have to provide a really, really sounding or relevant scientific motivation. But this is the reason. They are very, very heavy and very, very slow to transfer. Quick notes about ExoMars TGO. You will see a couple of images on Thursday. This was launched in 2016. It has lots of instruments inside. One is Cassis, which is a color and stereo imaging system. And this is how it works. It has a rotor on the telescope. So the telescope is observing at a slanted angle the surface. Once it's arriving on the top of the nadir, the telescope is rotating on the other side and then observing a surface on another direction, creating the stereo angle and creating then the topography. A nice thing is that we will have stereo topography using all the color channels of the camera. So meaning that you will have a panchromatic channel in basically in grayscale at this wavelength at 650 nanometers, then an infrared channel, a near infrared channel, and a blue-green channel, same as high rise. So it's also good that these two instruments are playing together. So Cassis can be a good complement for high rise, and everything can be put in context by CTX, which can be put in context with, for example, MOLA data. So it's also good to work at different resolutions from a broader to narrower, and then co-registering and playing up with all the capabilities of such instruments. The data are available at the ESA PSA, which is the Planetary Sensor Archive of ESA, but also in other repositories, which I will show you later. This is one of the first images taken up by Cassis. You will see like a CO2 frost on the slopes of a crater near, I think, the North Pole. It's Korolev crater. So this is colorful information in 3D, so with stereo topography. The resolution is 4.5 meters. The stereo topography more or less has 12 meters resolution per pixel, so similar to CTX. But nonetheless, this is a very, very powerful instrument. You will see it on Thursday with your hands. If you downloaded the Mars product, the Mars GIS project from our data repository for the school, you will be able to see it already. This is the coverage, so it's quite limited. It's increasing very fast, but again, since the instrument has to rotate, has to do lots of operations to acquire stereo images, it takes a lot of time, and again, you will have to have very, very high motivation, scientific motivation to acquire images around the planet. A brief introduction to spectral images. We will go there later on, but just to give you an idea what we can do on Mars, also on the Moon. This is an example of a Prism data cube. This is a spectrometer orbiting around Mars. Basically, you can create summary products highlighting different types of minerals. Why and how? Basically, every surface is reacting differently to the light spectrum, okay? This is the light spectrum, electromagnetic spectrum. And we can have multispectral imaging if we're taking very specific windows within the electromagnetic spectrum, separated one to each other, but meaningful for specific minerals. Or you can have hyperspectral images, meaning that you can have so many bands, one close to each other, that basically you can mimic a continuous spectrum along the electromagnetic spectrum, creating a fingerprint of a surface with specific peaks in the electromagnetic signal and absorptions. Every mineral has different peaks and absorptions, and this is giving basically the fingerprint of a mineral or of a material on the surface of a planet. Prism is what is called a cube. A cube is basically this. You will get an image on the surface of a planet, but inside the image, you will have different layers stacked all together, which are actually all the wavelengths together. Each wavelength is a slice of the cube. If you put them together, you combine them together, you can create a beautiful color composite, highlighting specific type of minerals. This is how the instrument appears. Very, very complex optical design. It has two detectors, one in the very near infrared, close to the visible spectrum, and the other one in the infrared spectrum. This is the spectral range. It's very, very technical information, but still it's good to know. It's a high resolution, hyperspectral image. So I talked about Mars Express. It was on board not only the HRSC camera, but also an Omega spectrometer, which has a resolution of about 300 to 1,000 meters per pixel. So one pixel is more or less half a kilometer or a kilometer wide. So it's good for observing large-scale objects on the surface of Mars. It is very much less good to observe very, very specific objects. Whereas Prism targeted observation, again, you see the targeted word here. It means that you cannot cover the whole surface of Mars with Prism, but you have to target the observation because they are very heavy and very difficult to take. But nonetheless, the resolution is basically 100 times higher, okay? So we will arrive to 15 to 38 meters per pixel resolution. And you can also pan sharpen the images with the high-rise panchromatic images to get these products here. They typically have this hourglass shape because the detector is actually moving onto a slit, doing this, okay? And so while moving, it's creating this when it's calibrating and then adjusted to the features observed on the surface of Mars, we will get to this hourglass shape. The products that we will use are called NTRDR, which is a complex acronym which stands to Map Projected Targeted Reduced Data Records. So the name speaks for itself. Basically, it's a full spectral range, joining the two information coming from the two different instruments. So the very near infrared and the infrared wavelengths are put together inside a single spectrum. It's already geometrically corrected, so you will get this hourglass shape, meaning that you will be able to match the features you observe on this Prism image to the actual shape of the objects on the surface of Mars. It's already corrected for the atmospheric absorption that you still have on Mars, although the atmosphere is very, very low density. And you also get removed the bad or suspect bad bands that are basically creating artifacts or misleading information. And this is how a spectrum appears of Prism, with some absorption and some peaks and so on. And NTRDR are currently the best available data. You can download them directly ready for JS in .img format. So now, how to download this data and how to consult this data? Let me go back. There are quite a few ways. A good way to do that in a first instance is using Google Mars, okay? If you have the application, so the standalone application of Google Earth, you know that there's a button here where you have Earth, Sky, Mars, and Moon. If you click on Mars, you will get to this. You have the globe, you can turn it around. This is the, let's say, the visible colors of the Mars globe. And you have some place names for your convenience, but you also have other options. For example, global maps. Global maps is the first consultation level that you can have. If you open this drop-down menu, you will get the visible imagery, the colorized terrain, which is basically the molar topography, so the Mars orbital laser altimeter topography wrapped around the Mars globe. We also the elevation information with the color coding of the elevation information. For example, here 21 kilometers in white is the top of the Tarsis Mountains, for example, the Olympus Mons, whereas the blue part are the much more depressed areas, for example, -6 kilometers inside the Valles Marineris. You will get a very nice information. You can also create topographic profiles. It's not the objective of this lesson, but you know that you can also do that on the surface of Mars using this layer here. You will get also the CTX mosaic. So the 6 meters per pixel resolution mosaic of Mars. If you toggle this layer on, it's quite slow because it has to suck from the server all this data. But you see all the different strips of CTX wrapped around Mars. If you zoom in, you will see how high the detail is of this CTX mosaic. And this is a good way to consult.
So sorry, Ricky, if I interrupt you. Actually, we are running with a bit, not late, but we switched to talks, so which means that we will have a bit later the break, just for information for everyone.
Okay, yes, it is. Also, I forgot to mention that we switched to talks. So how much time do I have left, Angelo?
50 minutes, am I correct?
I think it's more than enough, yes.
Yeah, okay, cool.
Okay, other layers is the infrared images. Infrared images are collected in daytime and nighttime. Okay, daytime infrared images are basically infrared images taken during the day, so you will get the shadows and the light areas. Nighttime infrared images are very, very interesting because you can observe Mars surface at night and you can measure the thermal inertia. So how much heat do the rocks release during the night? So the brighter the rocks appears, the more heat they are releasing during the night. And vice versa, if they appear dark, that means that they release the heat very, very soon, very, very fast. As you go, for example, on the beach, during the daytime, the sand is very hot, you can burn your feet, but during the night, the sand is the very first thing that becomes very cold. And this is how it appears. So you see how different, for example, some impact craters appear in the night. This is the loose material and all the ejecta layers and the ejecta blanket around the craters. You will get rid of the shadow information caused by the daylight, which is also good for some types of information. And you can play between the two to observe different things in a different way, which is also good if you want to mark some specific contacts onto a geologic map. For example, the ejecta rays are very, very much bright and visible in the nighttime infrared, very much less visible in the daytime infrared, or in the visible panchromatic channels taken during the day by the other instruments. So it is also good. Another good thing is that you can consult very quickly the spacecraft imagery. If you switch this on, you will get a high-res image browser, CTX, MOC, HRSC, and CRISM. For example, if I switch this on, if my computer collaborates, you will get, for example, here, a footprint of a high-rise. Okay, if you click here, you will get a preview of the high-res image. You will get some information on when it was taken, 29th of January 2014, the location, small description. And if you click to the observation information page, you can jump there in your browser. I hope that's working, but it's not working. Anyways, you will find the information on my slides later on, and you can then consult the images and then download them ready to be ingested into JS project. And this is true for every other instrument, for CTX, for MOC, for CRISM, for example, here. Let me see, here you will get CRISM data. You will see this hourglass shaped footprints that I shown before. This is where you have the spectral images of CRISM. Again, here you get the description, a small overview of the hourglass image, and then you can jump in to the specific website and download the image. Here it is. It's also opening inside Google Earth, so it's very convenient. You can consult the image layers, and you will get also some summary products. For example, the amount of oxidized iron minerals, the amount of mafic minerals, bound water, CO2 ice, hydroxylated silicates, abundance of sulfates, and so on. You can download the PNGs just for quick consultation, or you can download also the actual products from the top here. You see, there are lots of links that you can download all the images. This is a good way to consult the images. Another way is to go here to the ODE, Orbital Data Explorer. This is containing so far the data of Mars, the Moon, Mercury, and Venus. So let's talk, for example, about Mars, since we have seen Mars so far. If you click here, and again, you will see all this information inside my presentation when I will upload it to Indico. You will get product search, map-based search, which is, I think, the most useful one or the most intuitive one. You will get to a map interface. You can select the different types of base maps. For example, I want to have the molar topography, yeah, and the shaded relief together. And for example, let's say I want to go around Meridiani Planum to download some images about the landing site of Opportunity. Here you have some search buttons. You can search with a rectangle, with a point, with a polygon, and here you have two other buttons. So you can either display all the products inside your map frame, or you can decide to display products inside your search area. I normally use this one. Let's say I want to download some images from a Mars Reconnaissance Orbiter, for example, HiRISE of this crater, for example. So I can select products with polygon. I can create a polygon here. I release the button, and then I can select HiRISE derived products. I want to check if we have HiRISE images here. I click here, and you will see that the footprints of HiRISE appear. So it means that here we have HiRISE products. I want to see also if we have pre-prepared ETNs by the team. So you can click here and see we have none here, but we have nonetheless lots of images. And we can also check for other instruments, or we can check for other craters. We can start a new search here. Here we have just two images. So when you have selected what you want, you can click to view, and you will get the cart. And basically you go shopping. You go shopping like you are on Amazon. You have your product selected. You can have the color information, the red information. You can have a quick view so that you can check in real time your image. Okay, if it's good for you or if it's not good for you. And then you can toggle on what you want. It's going to be put in your cart, or you can add all the results to the cart. Then you go to the cart here, download. And then it's summarizing something for you. How much products you selected, the disk space they are going to occupy. If you want the right files, for example, the KML footprints to be put onto Google Mars, the footprint, the shapefile to be put into GIS, and so on and so forth. And then you can continue to the checkout. There are different options. Advanced user options, you can download the HTML product list, text product list, which I can do it for you. And this is basically downloading the URL of each image. So if you're acquainted to using like terminal in Linux or any other system, you have here all the URLs of the products. And actually, you can download all of them. You can select which ones. By the way, the good ones are the one with .emg file inside. Or the simplest way is probably to go back and to continue with the checkout. You can select the type of package that you want, the structure, if you want all the data placed inside one folder, which is called data folder. This is the structure of the folder. You put your email inside here, you submit the request, and then after half an hour, 2 hours, depends on how much data you ask for, you will get an email with a link. And through that link, you can download a zip file with all the data inside the data folder. So you download the zip, you unzip it, And inside you have many folders, data folder, browse extras, derived files, etc. And inside the data folder, you will get all the data ready for your JS project. It's very, very convenient. Another tool that we have from USGS is the pilot tool. This is specifically related to images. So not spectrometers, not laser altimeters, just images. The nice thing is that it's covering the whole bodies of the solar system. Let's go to Mars because I just talked about Mars. So just to show you the difference, it's also a map-based search. Here we can select all the instruments that observe Mars with images. For example, MRO. We want to check whether we have CTX images. It says that we have 132,000 images. So we have to go to the map search. We will get prompted to, again, a map-based web interface. We can select here the type of base map that you want, for example, in the nighttime or using the monotopography. Here you can set a bounding box, for example. You can do it by you can do it by creating a polygon, for example, around this volcano here. And then here on the right, you have all the images inside this specific bounding box. If you go here to this button, you can display, hopefully it works, maybe it's too much, display all the footprints of such images inside your specific box. I think I am asking too much now because, yeah, you see how many they are. If you want to check a specific single image where it's located, you can click on the single image balloon here, and it's showing its location on the top of your map interface. You can here, clicking on this small sheet, have all the information you need. For example, if you are interested to specific illumination conditions, here you have all the information you need. The ground resolution, solar longitude, incidence angle, etc. And then you can also download the single image from here. You can click here, and then you will download it for you. Or you can select many more, like here at the top. And then you can go here, you can select lots of products. And again, there are different options. You can download a CSV file that you can open in Excel, for example, with all the URLs, so the web address to download the images, a bash script with wget calls for the ones loving terminal like me, or projection on the web, which is another good service provided by USGS. It is basically map projecting the images for you the way you want, using all the information that Angelo provided in the talk before mine. You can simply click go. You can submit this, and then you will jump to this page that you have to register to if you're not registered already. Or you can provide your email. Files to process, and then you can, if you insert your information, then you can select the type of projection, whether you want the background removed or not, the type of format, if you want to have it in PNG, in TIFF, in ISIS format, in PDF format, and so on. And then again, you will get an email with the links for the images to be downloaded, ready for your JS project. So these are basically most of the user-friendly websites. There are many more. There's not much time to touch all of them. I just want to show you that USGS is also providing for you what is called Astropedia. So basically, it's a collector of information here about the solar system bodies of high-level products. So, for example, the mosaic of HRSC DTMs together with MOLA, or some mapping products as well, ready for you. For example, some specific type locations. There are the maps in JS format that you can use as a reference to build your own map. and so on and so forth. And this works for many bodies of the solar system, or for example, specific VTMs created with CTX of landing sites, for example, Jezero crater, and so on. So if you want to dig inside this Astropedia website, it's very good. You can select JS-ready files, historic maps, topography, the type of instruments. It's really, really granular, and you can get lots of information and pre-prepared data for you to use. So if you're not willing to process lots of data, this is also a good way to start to search for high-level products to base your work on. Again, here you can download the global products of LOLA, the laser altimeter, the wide-angle camera topography, the MOLA that I shown before. You can download all of them from there. And you can also use WMS capabilities, so meaning you can stream your map inside QGIS. There's no time to do it now, but there are the instructions inside my presentation. When you will see QGIS, you will see also how you can use this type of information. And you can basically ingest all this type of information inside QGIS. You can stream your map without downloading tons of gigabytes of data inside your computer if you don't have enough disk space. So basically, you can open your GIS and you can stream the information if you have a good internet connection, and you can create your map.